So let's start off with some sample diploma questions. So as usual, you can pause it here if you would like to try it on your own and give it a go. So in diagram 1, it shows you a magnetic field between two oppositely charged poles, and the arrow represents a magnetic field strength. So the length of this arrow is the magnitude of the magnetic field between north and south. Okay, there you drew the direction on you. So now we're going to stick a current carrying conductor inside of here, and it says which of the following diagrams drawn to the same scale as diagram 1 represents a net magnetic field at point P. So this guy here is going to create a magnetic field around it. So I'd probably use the first left-hand rule and stick your thumb going into the screen. And then if you curl your fingers around, you'll see that around here that it goes in a counterclockwise direction. Make sure you use your left hand. So what we're concerned with is we're concerned with the magnetic field at the top here. Right, so the magnetic field at the top here is going this way. So this is a magnetic field from the permanent magnets, and then we also have a magnetic field from the current carrying conductor on top that's going that way. So those two are going to add together and create a bigger magnetic field. So D is the correct answer. And then this one, a current carrying conductor that is that long and has a magnetic field of that. During a 20-second time interval, that many electrons pass the point in the conductor. Determine the magnetic force. So we need to use Fm equals I L B. And the first two parts of this is easy. The length is 4 times 10 to the negative 2 meters. And the magnetic field is 6 times 10 to the negative 2 Teslas. But the current we have to do a little bit of work at, right? So we have to use current equals charge over time. And what we need to do is we need to turn that into a charge. So we know the charge of 1 electron. So 1.6 times 10 to the negative 19 coulombs is the charge of 1 electron. And now we have 7 times 10 to the negative 19, or positive 19, sorry, electrons, like that. Electrons will cancel out with electrons, and we'll end up with a charge in coulombs. And we need to divide that by our 20-second time interval. So if I do that, 1.6 times 10 to the negative 19 times 7 times 10 to the positive 19 divided by 20, I get a current of 0.56 amps. And if I multiply all of those together, I end up getting an answer that is 0.001344. So one's in scientific notation, so it's going to be 1.34 times 10 to the negative 123. So that's going to be our answer for that. Okay, so moving charges in B fields. So lots of curriculum points. We're going to compare gravitational, electric, and magnetic fields because we're almost done all of this, so we're going to bring it all back together. This is just talking about how charges move in a field. Same thing. The curriculum points on this are kind of wordy. We're going to use the third left-hand rule again, and we're going to talk about a curved path in a magnetic field, and we're going to use free body diagrams acting on an electric charge. Okay, so here I have another video. I hope you liked that video, the first video. It gives a good another explanation. So Deirdre's back, and she will help you and guide you through these next questions. So I'm just going to insert the video here and enjoy.
so far we've discussed two factors which influence the strength of a magnetic field around a straight, current-carrying conductor.
The current through the wire and the distance from the wire, right?
Right, Deirdre. But there's a third way to intensify the magnetic field around a wire, by not making it straight anymore.
What do you mean?
If the wire is bent into a loop, the magnetic field is intensified. Using the left-hand rule for a conductor, we see that the loop may be thought of as a series of segments, each an arc of a circle, and each with its own magnetic field. Notice that inside the loop, the field is always out of the screen. Outside the loop, it is always into the screen. The net magnetic field inside the loop would be the cumulative effect of each segment and is therefore strengthened. Any ideas on how we could make the magnetic field even stronger?
Just add more loops to make a coil?
Yeah, when a current flows through the coil, the field around all loops will be in the same direction, and add to make a really strong magnetic field.
Right. This coil is also known as a solenoid or electromagnet. We use a modified hand rule to predict the direction of the field we get when a current is applied. Now, Anthony, you helped us the last time with the left-hand rule for conductors. So, Deirdre, it's your turn.
Ready?
Okay. Once again, electron flow is...
From the negative terminal to the positive.
So in this case...
It's like this.
Good. Now, Deirdre, take your left hand and put your curled fingers in the direction of electron flow.
Got it.
Okay. Notice that your thumb points in the direction of the magnetic field within the coil, and as a result, to the north end of the electromagnet.
Okay. The left-hand rule for the coil is different than the left-hand rule for the conductor.
Yeah, the left-hand rule for a conductor uses your thumb to show the direction of electron flow, while your curled fingers show the direction of the magnetic field.
But this rule uses your thumb to show the direction of magnetic field and your curled fingers to show the direction of current.
You're right. So you have to be very careful to use a proper hand rule, either the one for a straight conductor or the one for a coil.
I like lots of bass.
I know you like lots of bass.
Now, let's use our new hand rule to explore the magnetic field within an electromagnet.
All right. Let's say the electron flow through the coils is in this direction.
Then, using the left-hand rule for coils, the magnetic field generated inside the electromagnet would be in this direction.
And so would the North Pole.
Good. Now, what would happen if we reverse the direction of the current?
The direction of the magnetic field lines would also be reversed, as well as the North and South poles.
What do you observe about the shape of the magnetic field lines within an electromagnet?
The iron filings within the coil seem to be fairly evenly spaced and aligned.
Yeah, but at both ends of the coil and at the sides, the pattern is more jumbled and the filings are more spread out.
In fact, the field lines within an electromagnet are straight, almost equally spaced, and all point in the same direction.
So the field is uniform then?
Within the core of an electromagnet? Yes, it is.
Yeah, but as we move from the core of the coil to the ends and the sides, this field must become non-uniform and weaken. Look at the pattern of the iron filings.
The magnetic field lines surrounding the coil look a lot like the ones around an ordinary bar magnet.
Right, and both have north and south poles. Maybe that's why it's called an electromagnet. It's just a special type of magnet.
It is a special magnet, used whenever you want to produce a strong magnetic field. Tell me how this little gizmo works.
Well, this air core electromagnet is hooked up to a power supply. When I close the circuit by pressing this switch, The electrons flow through the coil and induce a magnetic field in the core of the electromagnet.
And using the left-hand rule for coils, we found the coil's north pole.
A magnetic field is also induced in the iron nail because it's so close to the electromagnet. The top of the nail is south.
And because opposite poles attract, the nail jumps.
I see. And when the circuit to the electromagnet is open, the nail falls. Quite the apparatus. Here's something else for you to look at. This is a request exit switch. Why do you think you have to push it before opening the door?
You only have to push it after hours, so the alarm won't go off.
It's true, it deactivates the alarm, but it also does something else. When the switch is pushed, the circuit to an electromagnet housed in the door strike is complete.
So then a current flows through the electromagnet and it's magnetized.
But wouldn't that hold the door closed if the latch is ferromagnetic?
No, there's a pin that prevents the door strike from releasing the door.
I get it. The pin is similar to the jumping nail. A force is exerted on the nail because of the interaction between the electromagnet's magnetic field and the nail's own induced magnetic field.
A magnetic field is also induced in the pin because it's so close to the electromagnet.
And the electromagnet pulls the pin out of the way, allowing the door strike to move, and we can open the door.
Right. But the electromagnet is only activated for a short time, so we'll have to move fast. Ready?
In later years, Hans Christian Ørsted claimed that his discovery of the relationship between magnetism and electricity was not an accident. But whether it was a lucky coincidence or the result of careful scientific inquiry, Ørsted's revelations dramatically changed our world in motion. Okay, now you can crank it up.
Okay, so now let's get to our new lesson. So, charged particles like current carrying rods, I don't know, I switched to rods there instead of conductors, experience a magnetic force when moving through a magnetic field, right? Electrons are moving through this wire, so they experience a force. Well, if you just shoot an electron through, they'll also experience a force. Since current is a flow of electrons, the movement of one electron or any charge, positive or negative, alpha particle, whatever it is, we can figure out that force on that. Okay, so to find the magnitude of the force, we can figure that out from our old formula. Fm equals, oops, I don't know why I did the equal sign there, I'm tired. Fm equals ILB, and we can break down our current as charge per time, and then leave length in B. And if we focus on these ones, so length is just another term for distance and time. So if we have distance over time, we can say, oh, well, that's B, right? And keep Q and B the same, and voila, we have a brand new formula, and this is on your formula sheet. It's just below the one we learned yesterday. And it's Fm equals QVB, where this is the charge of the charge moving through there. This is the speed of the charge, and this is our magnetic field. So for electrons, the direction of the magnetic force follows the same rules as that third left-hand rule. But now we can throw protons or alpha particles which are positive, and they follow that conventional current. So an easy trick for doing that is, instead of using, well, they're going to be opposite direction as a positive charge, electrons will be. So this means if it's positive, we're going to use our right hand. Okay, if you use your right hand, it works for positive charges. So let's jump into an example. Determine the direction, the magnitude of magnetic force on an electron that's traveling at a velocity of 3 times 10 to the 6 meters per second into the page through a 6 Tesla field. So our magnetic field runs from north to south. Our electron is going into the page, so we can determine the direction of our force. Here we go. So we'll draw. This is the direction of our magnetic field that we had there, and we're going to use our left hand because it's an electron. So we put our thumb going into the page, right? And there we go. So my thumb is going into the page, my fingers are pointed over to the right, and you can see that if I use this as my electron right here, I'm going to push it up. So the answer is up. And then what we can also do is we can determine the force. So we can use our Fm equals QVB formula, and charge of an electron is 1.6 times 10 to the negative 19 coulombs. It says in the question that the speed is 3 times 10 to the 6 meters per second, and that the magnetic field is 6 Teslas. So if we plug that into our calculator, 1.6 times 10 to the negative 19 times 3 times 10 to the 6 times 6, we end up getting 2.88 times 10 to the negative 12 newtons, and that is up. So we have a magnitude and we have a direction. Okay. So what would be the magnetic force if it was a proton? So if we go back to this, if it was a proton, the only thing that I'm going to change is instead of using my left hand, I am going to use my right hand. So again, I'm going to make my thumb go into the page, and then I'm going to make my fingers go this way, right? And you can see that now my hand is pushing down. So it's going to be, for a proton, it's going to be down. And if we look at our numbers, well, the charge of a proton and electron are the same. We can look that up on our data booklet. The speed is the same, the magnetic field is the same. So it's going to be the same magnitude. It's just going to be down instead of up if we use a proton. So this board question, so we can just practice that third left-hand rule one more time. So we have, let's write this down, a force that is, we're trying to find, the magnetic field is up, and then it's a proton direction is west. Okay, so I'm going to go to my board here. So I'm going to write on my north, east, south, and west like that because we're using west in the question. So it's a proton. So first thing I'm going to do is grab my trusty right hand, and I want my direction of my thumb, which is my proton, to be going to the west. My field is up, so you can see that my palm is pushing it to the north. Okay, and yeah, pause these board questions, try it yourself, and then watch me go through it. So let's try another board question. So this time we have a force that's south, we have a field that's down, and we are trying to find our electron direction. That's what we want to know. Okay. So pause the video and try it yourself. Okay, so it's an electron, so I'm going to grab my trusty left hand. So my force is south, so I'm going to make my palm push it south, and my field is down. Oh, I'm already in the right direction, so my field is going down, it's going into the page like that, and you can see that my thumb is pointed east, so that's our answer, is it's going to be going east. Okay, let's try one more of those. So this time we have force is out of the page. So different reference. Magnetic field we don't know. And we want alpha. So an alpha is positive. So we want to use our right hand for this one. So let's try this out. So my trusty right hand is what I'm using in this one. My positive direction, my alpha particle direction is up, and my force is going to be out of the page. So the board is my page, so I'm going to be going out of the page. So you can see that my fingers are pointed north, but most of the time, oops, sorry, I did that incorrectly. Let's try that again. So my proton is up, and my force is, sorry, this is up. I'm a little bit confused because I'm looking at it a little bit differently. Sorry, this is upwards, and then my force is out of the page like that. Sorry about that. So force is out of the page, my thumb is up, and you can see that my fingers are going west, but more often than not when it's talking about out of the page, we're going to say that's going to the left of the screen. So my answer would be left. There we go. So hope those are good. And again, if you have any questions, let me know. So I have another board question. Determine the force on the charged particles when entering the three different fields. So pause the video and I will go through an explanation. Okay, so for electric fields, the direction of the field, how do we figure that out? Hey, it's me, Pedro. Don't forget about me, it's been a while. I'm always here. So Pedro is going downwards. So if Pedro is going downwards, it means there'd be a positive plate up here and a negative plate down here. So if we're sticking an electron through there, then that electron is going to go, it's going to experience a force upwards towards the negative positive plate. Okay. So pause the video for magnetic field. So for magnetic field, I'm going to draw this one out on here. So my magnetic field is going downwards like that, and my electron is going that way. So I'm going to switch screens here to this one. So it's an electron. I want to use my left hand. I want to make my thumb go that way. I want to make my fingers go down. So you can see that my palm is out of the page. So my force for this one would be, we could draw a little dot for it. So that's a dot, and that's out of page. Page. Start to write with the thing. And this last one, gravitational field. So give that a go. So for my gravitational field, this would be like the ground. And although an electron doesn't have a lot of mass, if there's no other fields acting on it, eventually that electron is going to go towards the ground like a projectile. So this one would be down. The diploma loves these questions, which means I love these questions, and it's going to be on a test. So make sure you know how a particle would be affected in each of those three fields. Okay. So an electron traveling at that speed enters an area with a perpendicular magnetic and electric field. Ooh, we have magnetic and electric field with a strength of 500 newtons per coulomb and passes through undeflected. Draw a free body diagram of the forces acting on the electron and determine the magnitude and direction of the magnetic field. Cool. So we have in the picture, we have a positive plate above, and we have a negative plate down below. So if we send an electron through, that electron, actually let's draw the electron in the middle here, that electron is going to be attracted to that positive plate. So that means that this is my electric force, which is upwards. So it says that the electron passes through undeflected. So that must mean that there's another force going downwards. And because we're talking about an electron, a subatomic particle, it's going to be a magnetic force and not a force of gravity. Because its mass is so small, when we have other forces there, that force of gravity is going to be insignificant. So these are going to be our two forces. If it was an oil droplet, like those type of Millikan questions, then the force of gravity would be important. But this is an electron, so it's just going to have these two forces. So what we can say is Fe is equal to Fm, and we can break this down into QVB, and then we probably forget this because it's been a while, but this breaks down into EQ, right? And our charge cancels out there. So we want to find the magnitude of our magnetic field, so I just move my velocity down there, and I can plug in my numbers. It tells me that I have a 500 Newton per Coulomb electric field, and my speed is 2.8 times 10 to the 5 meters per second. So to find my magnitude, 500 divided by 2.8 times 10 to the 5, I end up getting 1.79 times 10 to the negative 3 Teslas. And then in terms of direction, well, my electron is going this way, right? And it's experiencing a force that's downwards. So it would be into the page is which way my fingers are pointing. So it would be into the page. So something that we're going to add on to this is spiraling charges. So the magnetic force on a moving charged particle in a magnetic field is always perpendicular to the direction of motion. So as the direction shifts, so does the FM. It continually shifts to remain perpendicular to it. So what I mean by that is if I have an electron that's going that way, and say my magnetic field is into the page, what's going to happen is my thumb is going to go this way, my fingers go that way, and it's going to push it down. So as it gets pushed down, it's going to start to travel that way, and that switches the direction of my thumb. So now I'm pushing like this, and now it's going to be going downwards like that. And if it's going downwards, my magnetic field stays the same. I'm going to push inwards. And what that causes it to do is it causes it to move in a circle. So this makes the particle's direction curve into a circular path. So these terms come up on questions, parabola versus a circle. So a parabola is when the force is constant, it's a constant direction. That's when it moves in a parabola. So this was an example of something that's moving in a parabola. So the force is acting on this if it's going downwards. It's just an electron, so it experiences a electric force, and the whole time, no matter where it is, it's a uniform field, so it experiences an electric force that's downwards, and that direction doesn't change, so it moves in a parabola. For something to move into a circle, that was like the last example, and as the particle changes its direction, well, the direction of the force also changes, and that direction of the force is always towards the center of the circle, right? So it's always changing and always moving towards the center of the circle. So draw a free body diagram of an electron traveling in a circle. Well, I can do that as it's traveling in a circle. There's always going to be these forces at each position that go towards the center, and all of these are magnetic forces. That's what makes it move into a circle. So is the electron accelerating? So if something is accelerating, if it's moving in a circle. If you're moving in a circle, you're accelerating. So yes, it is accelerating. Is the electron's velocity changing? Well, yes, if you're accelerating, your velocity is changing. Is the electron's speed changing? Well, no. You can go in a circle at a constant speed, right? You can go into a traffic circle at 5 meters per second the whole time, but as it's moving in a circle, if it's moving 5 meters per second, here it's moving down, here it's moving right, here it's moving up, and here it's moving left. Right? It could be going 5 meters per second left, 5 meters per second down, 5 meters per second right, 5 meters per second up. So the speed, which is the number, isn't changing, but because the direction is changing, that's part of velocity, that's what makes it a vector, then yes, its velocity is changing, it's accelerating, but its speed is not changing. So let's do a circular motion style question. And this is our last question. Look at that. So an electron is accelerated from rest across a potential difference of 20,000 volts. It enters a magnetic field of 60 milliteslas that is perpendicular to the direction of the electron's path. Determine the electron's radius of the curvature in the magnetic field. Whew. Okay, so this is a big question. So let's draw out what's going on here. So first thing that happens is my electron is accelerated between two electric plates. Okay, and then we're going to make a tiny hole in this plate so that the electron can go through. So my electron is accelerated between plates here. So if it wants to be accelerated, it has to be where it doesn't want to be, by the negative plate. And here it's by the positive plate here. And then once it gets past that, it enters a magnetic field. The direction doesn't really matter, so we'll just say it's going into the page. And as it goes that way, and as it goes into the page, it's going to be deflected downwards, and it's going to start moving in a circle like that. So what we're trying to find is we're trying to find the electron's radius. So there's two different parts to this question. So for this part of the question, let's break this into two parts. So the circle and the acceleration. So when something is moving in a circle, that's physics principle number 2. And for physics principle number 2, we have to say, well, to make it move in a circle, what's making it move in a circle? Well, it's that magnetic force that's making it move into a circle. And you'll have to remember from the review, right, we have these formulas right here that show it moving in a circle. So Fc is just the same as Fnet, right? Fnet is equal to ma, but we put that little c when it's moving into a circle. And the acceleration is, we can break down into v squared over r. It's that formula right there. So that's how we get that circular motion formula broken down. And then Fm for a charge is equal to qvb. So we want to find this radius down here. So I'm going to move radius up top, and I'm going to move qvb down below. Right? One of these velocities ends up canceling out, so we end up with mv over qb is equal to r. That's how we find our radius. So the question gives us, well, we know the mass because it's an electron, we know the charge because it's an electron, and it gives us the field, but we don't know the velocity, and that's where we get it from this first part, right? So for this acceleration part, we can use physics principle number 5, which is our law of conservation of energy. We did these questions in the first unit. It's actually probably nice to review because it's been a while for you. So here it has that electrical potential energy, and then right before it leaves, it's going to switch into kinetic energy. So we're going to say that the sum of all our energies before equals the sum of all our energies after. Before we have electrical potential energy, after we have EK. If you remember this one, it doesn't look like EPE on the formula sheet. It's this one right here that says delta V equals delta E over Q. So it's going to be VQ. And that's voltage. We have voltage and velocity, so we want to be careful. I'm going to put my bars on there. This is 1/2 mv squared. So what we're able to do is we can find the speed from this formula. So we move the 2 up top and the m down below, and then square root it, and we can find the speed of our electron. So 2 times our voltage, 20,000 volts, times the charge of an electron, 1.6 times 10 to the negative 19 coulombs, divided by the mass of the electron, 9.11 times 10 to the negative 31 kilograms. And we type all that in. 2 times 20,000 times 1.6 times 10 to the negative 19, and divided by 9.11 times 10 to the negative 31. And I get a ridiculous speed of 10 to the 15 because I forgot to square root it. So you can't be faster than the speed of light, so make sure you square root that. And we get 838.16746.43 meters per second. Okay, so now we're ready to plug everything into here. So the mass of the electron, 9.11 times 10 to the negative 31 kilograms. Our speed is our 838.16746.43 meters per second. Our charge is 1.6 times 10 to the negative 19 coulombs. And our magnetic field is 60 millatesla. So milli is times 10 to the negative 3 teslas. And we can plug all that in. And our answer should be like a few centimeters because they're never that big of circles. So if you get a few centimeters, you know you did it right. Oh, millimeters. So we have our final answer. I'm just going to write up here. 7.95 times 10 to the negative 3 meters, or 7.95 millimeters would also be a good answer. Okay, so give that a go. See how that works out for you. This is a homework. It's a lot of homework, but we're not doing anything, and you got the whole long weekend, and I know you're not going to Grandma's for Thanksgiving dinner. Not Thanksgiving, Easter dinner. So you got a lot of time to work on it. So let me know if you have any questions. Remember, I posted the answer key a long time ago, so all the answers for these questions are in my Google Classroom. It's one of the first things that I posted, so check that out if you need it. And good luck, and thanks for listening, and have a wonderful long weekend.